Welcome to lesson 26. In this lesson we're going to build on what we've done in the preceding two lessons, HT24 and HT25, dealing with the question of solving for the heat transfer coefficient H for internal flow. So with that, let's begin. Solution of fully developed laminar flow in a tube. All right, keep in mind what our objective is. Our objective is to solve for the heat transfer convection coefficient. We're going to do that. As you know, we've introduced two cases so far, and today we're going to look at case number one. Case number one, of course, is where we have a constant flux for our on our surface. Okay. In order to accomplish this, we're going to need to do two things. We're going to need to use what we solved for in the preceding lesson, which is the mean velocity, and we're going to have to tie that in with the third of our equations. So we're going to solve for the partial of t with respect to r and Tm, that is the medium temperature, using conservation of energy equation, the last of our three equations, and the one that we have not used thus far. And that's going to allow us to solve for H. Using the energy balance at the wall, which we introduced some time ago. So we're going to use the conservation of energy. We're going to come up with an expression for dt dr, the partial of t with respect to r, and that will allow us to solve for H using the energy balance at the wall. Okay, so let's get started. The governing equation is the conservation of energy. And we're going to do this for the case of a tube, a circular geometry. So it's going to be a cylindrical coordinates. And it's going to be u times the partial of t with respect to x plus v times the partial of t with respect to r is equal to alpha over r times the partial with respect to r of the quantity r times the partial of t with respect to r. And you remember that from chapter 2. All right, now, let's not forget the other needed equation, and that is the energy balance at the wall. And of course, that is where we realize that the conduction leaving the surface has to be equal to the convection being carried away. And so what that yields us is this. H is equal to K times the partial of T with respect to R, evaluated at R equal R sub 0, that is at the surface of the tube, divided by PS, the tube temperature at the surface, minus the medium temperature. So if we move this up here, we have the convection per unit area must be equal to the conduction per unit area. That's our energy balance at the wall. So let's begin this discussion by examining the conservation of energy equation. Yes, did I misspell that exam? Here we are. Examining the conservation of energy. So we rewrite the conservation of energy. U times the partial of T with respect to X plus V times the partial of T with respect to R is going to be equal to alpha over R times the partial with respect to R of R times the partial of T with respect to R. Now we can do something immediately to simplify this equation. You'll recall from our discussion in the last two lessons, when flow is fully developed in a tube, there is no y component velocity. So that means V is equal to 0. So we can then rewrite this equation as follows. U times the partial of T with respect to X is equal to alpha over R times the partial with respect to R of R times the partial of T with respect to R. Now, from last time's class, for the case where we have a constant surface heat flux, you'll recall from last time's class that we were able to draw this graph of temperature versus distance down the tube. And this is our starting point, the fully developed region. From this point on, this is X, fully developed, thermally fully developed. Then what we have is the following result. We know that the surface temperature, the slope is constant. So that means that the change of the surface temperature with respect to X is equal to a constant. We also know that the medium temperature of the fluid, Tm, is also constant under those circumstances, and that the delta remains constant in the fully developed region. All right, mathematically, that is reflected as the partial of T with respect to X is equal to the change of temperature of M with respect to X, and those are both equal to a constant. So that says this is constant and equal to this. And so with that, we're going to make a substitution. And we get the following result. We're going to substitute for U of R from last time's class, as well as for T, a partial of T with respect to X. And we're going to get the following result. UM times the quantity 1 minus r sub 0, or excuse me, r over r sub 0, that quantity squared. And this is, of course, your u function of r from last time's class, times the partial of t with respect to x, but that's going to be equal to the change of temperature, the mean temperature with respect to x, which is a constant, which will carry through. And that's going to be equal to alpha over r times the partial with respect to r of r times the partial of t with respect to r. Now, we're going to go ahead and rearrange. We're going to say the partial with respect to r of the quantity r times the partial t with respect to r is equal to this times r divided by alpha. So it would be 2um divided by alpha. And now we're going to divide through by r, and that's going to be r minus r cubed over r sub 0 squared times the change of the mean temperature with respect to x, which again, I'll remind you is a constant. Now we're going to integrate. We're going to integrate this side. So the integral of the change of r dt dr is just going to be simply r times dt dr, partial of temperature with respect to r. We'll multiply each side by dr and we'll integrate. And that's going to be equal to 2um over alpha. And now we're going to integrate, and that's going to be r squared over 2 minus r to the 4th over 3 r sub 0 squared. 4 r sub 0 squared. Times dtm dx plus c1, constant of integration. All right, now we need to apply a boundary condition. We want to get rid of that. Here's how we'll do that. So we will apply the boundary condition. Which we'll call number 1. And that boundary condition is simply this. At r equals 0, which is at the center of the tube. Remember, r is 0 in the center of the tube, and r is equal to r sub 0 at the perimeter, around the edge. We can say that the change with respect to r due to symmetry is equal to 0. And of course, you've seen this before when we first started this section, of course. All right. So, if that's the case, we apply this to this equation. We have r is equal to 0, this is equal to 0, and r here is 0. So that means that C1 must be equal to 0, which is always handy. All right? So now let's integrate again. All right, so we have this term remaining with this. I'm going to divide both sides by r, and then I'm going to integrate the change of temperature, and this is going to be brought over here, and we'll integrate that side with respect to r. So on the left side of the equation, we'll have t, a function of r. And on the right side of the equation, we'll have 2um divided by alpha times And remember now, we divided through by r, so this is r over 2, and this is r to 3 over 4r0. So when we integrate that, that will be r squared over 4 minus r to the 4th over 16r0 squared times the change of the mean temperature with respect to x plus C2, the second constant of integration. All right. Now, we can apply the second boundary condition. And boundary condition number 2 is at r equal r sub 0, we have t equal to Ts, which we know is only a function of x. T is only a function at the surface, is only a function of the linear distance down the tube. All right, so that being the case, if we apply boundary condition number 2, we end up with C2 being equal to Ts, a function of x, minus 2um over alpha. We'll move the change of the mean temperature with respect to x there, and we are left at this point with 3r0 squared over 16. So that is our value for C2. So the final result is as follows. T, a function of r, in the fully developed region of tubular flow, laminar flow, is equal to T, let me rewrite this. This is a function of both x and r, because we know that the T changes as it moves down the pipe, although we have eliminated that through keeping this as a constant here. So we have Ts, a function of x, plus 2um over alpha times dTm dx times the following: r squared over 4 minus r to the 4th over 16 r sub 0 squared minus 3/16 times r sub 0 squared. And this is equation 850 in your textbook. Okay, so what did we want to do? If we remember back to the first board, you will see over there that we wanted to solve for an expression for the change of temperature with respect to R using the conservation of mass, or excuse me, the conservation of energy. We have done that. But the next step is to take this solution and to put it back into the energy balance at the wall to see if we can come up with a value of H. Now, I admit at this point right now, you're probably saying obtaining a value for H for this is going to be quite a chore. But you're going to be surprised at how this all works out, I guarantee you. So now let's examine the energy balance at the wall. All right, partial of T with respect to R, this equation right here, this term goes away. because the surface temperature, while a function of x, is not a function of r. So that goes away, and now we look at this term right here. This remains a constant. And now we need to take this term with respect, the derivative of this with respect to r. Well, this term, this portion of the term is going to go away because r is not there. So we're going to be we're going to be left with 2um divided by alpha times dTm with respect, the change of the mean temperature with respect to x, times r over 2 minus r to 3 over 4r, 0 squared. And this is, then we evaluate this at r equal at the surface, and we end up with 2um over alpha times dTm dx times r sub 0 over 4. So all of a sudden, this is looking a little easier. Okay? What do we do next to complete this? You'll recall from lesson 25 last time's lesson. We came up with an expression for Tm, the medium temperature. And we said Tm was equal to 2 over um times r0 squared times the integral from 0 to r sub 0 of u times t times r times dr. This was equation 826. Now we have an expression for u, which we can substitute in here. We now have an expression for t, which we can substitute in here. And then we can perform this integral. And if we do that, we get the following result. I'm not going to do it here. I'm going to show you the following result. So substituting, for u and t, and differentiating, we have the following, again, gets results in the following. And that is Tm, which is a function of x only, we already know, is equal to Ts, a function of x only, minus 11/48 times r sub 0 squared over alpha times the change of the mean temperature with respect to x. And this is equation 851. All right, so now we substitute this into the energy balance at the wall. And we get the following result. H is equal to K times the partial of T with respect to R, which we know is 2um over alpha times dTm dx times r sub 0 over 4. over TS minus TM, which gives us 11/48 from this equation, times UM times R0 squared over alpha times DTM dx. And if you simplify this, you can see these terms go away, the UMs go away, the alphas go away, and you have R0 here and R down here, and you have a 2 up there, and what this turns out to be is H is equal to 48/11 times K over D. And therefore, the Nusselt number as a function of D is equal to HD over K, or this turns out to be, the Nusselt number turns out to be 4.36, which is equation 853. This is the Nusselt number for the following conditions. Let's remind ourselves. Laminar flow. Fully developed flow. Constant properties. And lastly, Qs of the surface, the heat flux, being at the surface being constant. Now, open your books to table 8.4, and you will see that the second entry in this table under the correlation is the Nusselt number. The equation is 853, and the conditions for that are laminar, fully developed, uniform, or constant surface heat flux. That's how it got there. The beauty of this, like the Blausius solution, is this solution is based on an analytical first principles analysis using the conservation of mass, conservation of momentum, and conservation of energy. And lastly, the energy balance at the wall. You can see, if you look down to the next line, you'll see the Nusselt number is equal to 3.66 for laminar flow fully developed with a uniform surface temperature. The derivation of that is similar in nature to what we just did, but we don't have time to go through all that today. I will write up here, however, that a similar solution exists for case number 2. Ts is equal to a constant. And of course, if you recall from last time's lecture, that's going to look something like this. And Tm looks like this. And that solution yields a value of a Nusselt number equal to 3.66. I look forward to seeing you in class about a week from now and answering any questions you might have.